Hi, how are you?
Oh, very good. How are you?
Yeah, I'm good. Okay, let's start our discussion. Okay.
Okay.
I'm what I got, what I get from your audio note that you have to learn filter first, right?
Hmm.
From the basics.
The filter is also not Butterworth and all those things because it might take some time, right? At least to start with the
Low pass and all
just
those things, right?
hmm.
Yeah. Yeah, basically the document that you have shared, I have to go
Hmm.
through those, right?
Hmm.
Yeah.
Correct.
Okay. Who will take?
Some some theory first for that, Abhishek, and
Yeah,
then
yeah.
we'll you help me with the steps which I can use for to solve these problems and remember the steps and but mainly first theory about it.
Yeah, yeah. First of all, we will take up the low pass filter, okay?
Okay.
LPF. Low pass filter. Okay. See, basically in our active filter, we used to have the three type of low pass filter.
You're not
Uh,
sharing the screen, Abhishek.
okay, sure. Basically, in the low pass filter, we
Hmm.
usually have three type of low pass filter. Okay,
Hmm.
that is active in the. If I'm talking about this, then active low pass filter. Okay,
Hmm.
three type of low pass filter: inverting low pass filter, non-inverting low pass filter with gain, and
Okay.
inverting low pass filter without gain. Let's me
Hmm.
take one of them. Okay,
Hmm.
let me take one
Before
of them.
that, before
Yeah,
that, Nitya,
yeah.
if
Tell
you
me.
prepare the key only for the kind of problems I've sent, that also is okay.
Yeah. From that only, I will be taking. I
Okay,
will
got it.
taking the examples of your problem only.
And then
Okay.
the theory only relevant for that because sometimes there
Right,
could be.
right, 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 right. First question is low pass filter. That's why I'm taking the low pass filter first. Okay.
Hmm.
Okay. And they have asked you. If I'm not wrong, they asked you non-inverting low pass filter, right?
I
Non-inverting low pass filter active, right? So
uh,
in
they just
non-inverting, we have two types. Sorry.
correct.
Yeah, in the non-inverting, we have the two type of non-inverting low pass filter. In the
Hmm.
active, if I'm talking, then it is active
Correct.
first order. There are two type, non-inverting with unity gain, okay, and non-inverting with gain.
Hmm.
I haven't specified that do we want non-inverting, inverting with gain or with unity gain. So I'm taking simple one, non-inverting with unity gain. Okay,
Got it.
I will
Hmm.
give you the circuit for the other one also. I don't know
Okay.
which is relevant for you. Okay, this
Hmm.
is your op amp. These are the active elements. You can, okay. This is known as non-inverting because we are giving the input at the non-inverting terminal. Okay,
Correct.
correct. And this is R1
Right.
and this is C1. Okay,
Hmm.
and this is your V output basically,
Hmm. Hmm.
right? Okay.
Hmm.
So this
Hmm.
is your non-inverting low pass filter. Do you want me to
Hmm.
go in the working or just
No, whatever theory is necessary for the dial. I mean, whatever minimal is required. I mean, if it's important, yeah, please go ahead.
yeah, I will just take 2 minutes for the theory.
Hmm. Hmm.
Okay. Now, what do you mean by low pass? Low pass means what? It should
The low
pass the
frequencies
some
it should.
low frequencies only, right? And it should block the
Correct.
high frequency, right? Correct.
Correct.
So,
Correct.
do you know the what is the nature of the capacitor? Will it pass AC or okay? Can you tell me the what is the nature of capacitor? Can you tell me?
The
Nature of the capacitor is
capacitor
that it
will
blocks
filter
the
the
low frequency.
yeah, it will filter the I mean AC to a little bit DC with the ripple thing, right?
Right. Basically, I want to say that what is the capacitor? What is the reactance of the capacitor? Can you tell me? This
1
we
by
can
2
tell
pi
that,
RF and all that is it, right? 1 by 2 pi
yeah,
RF.
1 by j omega c, right? If your frequency is high, your capacitance value will be low, right? This reactance value is very low, right or wrong? Right? So if your frequency is high, then your reactance value is very low. It means that this path will allow current to pass, right or wrong?
Right.
So for high frequency, the current passes to only the capacitor. It do not go inside the op amp. Okay. So that's why it is blocking the high frequencies. But for low frequency, what will happen? For low frequency, this reactance Xc value will be quite high. It means that this capacitor will be open circuit, will act like just open circuit. So
Okay,
all of the input will pass to the output. Okay. This is basically your low pass filter working. Okay. And its frequency is 1 by 2 pi R1C.
R1C.
Okay. Okay. Any doubt?
This
Okay.
j omega c,
Right.
that is impedance capacitance.
Yeah, of the capacitor. Yeah. That is known as
Impedance.
reactance. Yeah. That is known as
Reactance is
reactance.
almost like
Yeah.
like resistance, right? I mean, for
Right.
capacitor, but
Yeah.
meaning is the same, right?
Yeah,
And
meaning is same then.
this FC frequency equal to 1 by 2 pi R1C. C1, that I remember.
Right.
And
Okay.
the J omega, what is that formula? That reactance thing is?
See, reactance is Xc equal to 1 by j omega c. Okay.
J omega, what is the notation there? J is just a complex number, right?
J is the complex number. Right.
So it's like I in our complex
Right.
number. IWC for all purposes, right? And W and C is the capacitance.
W is the frequency. Yeah, the W is the frequency. W is frequency in radian. That is 2 pi f. Okay. And C is the capacitance.
Okay. It is nothing. Okay. It is the same thing there.
Right. Same thing there. Right.
W is just 2 pi f.
Yeah, in the radian, frequency in radian. Okay. Any doubt?
No.
Okay. And basically what they are asking, they have given capacitor value, right? They have given capacitor value for you, right? Right or wrong? That is nothing but 1.8 nanofarad, right? And frequency value is also given. That is 629 hertz, right? So can you tell me what will be the value of resistance? 2 into 3.14 into 1.8 into 629.
R1 value you're asking, huh?
Yeah, R1 value I'm asking.
Okay, so it will be 1 by 2 pi FC.
Yeah. You can calculate it, right? Or do you want me to calculate?
Yes. No, I calculate.
Okay, sure.
FC C1. Fourteen 26.12, huh?
Yeah, it may be. I didn't calculate it. I don't have a calculator. But yeah, it is straightforward, right? Okay. You can basically write R1 equal to 1 by FC 2 pi C1. This is your R. Okay. That's fine. This is for unity gain. Okay. Because we don't know what is the our circuit. So I am taking this is your low pass filter. Okay.
Okay. No, it's clear. Yeah. So it will allow the low frequencies, this circuit.
Right. It will allow only the low frequency component.
And there is no gain in it. That's what you're saying, unity gain. So how much ever the voltage is there, it's not amplifying it because the feedback resistance and all those things are not there.
Right. I will just give you the concept of other low pass filter also. That will be helpful for you, right? But for question 1, that is your answer. Okay.
Okay.
Just for information point of view, I'm just sharing some idea that non-inverting.
Just in case if they ask the other question also.
Right. Non-inverting
Gain.
with gain.
With gain means at the top you have to have the resistor and all that, right?
Yeah. Let me say.
Feedback has to be sent.
Right. So this is R1, this is R2, and this is your resistance. Right. R and C. This is your input, and here you are taking output. Okay. So basically, frequency is again 1 by 2 pi RC, and gain is 1 plus R2 by R1.
This is like a regular
Right.
inverting amplifier.
Right. Okay. Any doubt? Okay. We have one more variant, inverting amplifier with gain. Okay. Inverting LPF, inverting amplifier with gain.
I'm just wondering how to remember this, but anyway, I'll try.
Yeah, there is no, I will tell you that how to remember it.
Here capacitor will be there. This is the example that they gave, right? Next one is that one.
Yeah, in the question. Right, this is R1, this is R2, this is C1, and this is your input, and here frequency is 1 by 2 pi C1 into R2, and gain is what? Minus R2 by R1. Basically, we are finding, if I'm telling that gain, it means that DC gain. Okay. DC gain. For the DC, capacitor will get open circuit, and this is like that. Just capacitor will be open circuit, and it will be short circuit. Okay. Fine. Okay. Any doubt till now?
So minus R2 by R1 is like for any other
because it is inverting, right? Because it is inverting.
So that minus R2 by R1. I mean, even if I don't know, calculation wise, I can still do that, right? VO minus 0 by R2 equal to Vn by R1, right? So VO
right. In that way, you can find it.
Minus R2 by R1. Okay.
Any doubt?
No.
Okay. Let's take up the question number 2. Okay. Question number 2, what they are saying. In question, the filter has to be passband gain. Okay. If filter has to be a passband gain of filter has a passband gain of 6 volt.
6 V by V, I don't know what by means. 6 V by V. Something.
Yeah, V by V, it means that gain is always in voltage by voltage form, and feedback resistor R2 is given 57K. What is R1? Okay, filter has a passband gain.
So we should filter the low frequencies. We should filter the high frequencies, and then the middle one we have to send it. Correct?
Right. Passband gain of filter we have to calculate basically. Okay, let me show you that how the passband looks like. Okay. Here in the passband, we have to find this R2, right? It behaves like that. Let me show you. We have one op-amp. Okay, -2 plus. We will make low pass filter first. Okay, we will make high pass filter. Okay. This is your passband. Okay, this is your feedback register is R2, right? This is your R1, and here you are sending V input. Any doubt? This is your C2, this is your C1. This is C1, C2.
Because they asked with feedback, that's why we
Pass
drew
band
R1,
gain.
right? Or else we could have drawn another capacitor in parallel, right?
Where?
Like R1 C1 is there. Right? After that, another
Yeah.
capacitor in parallel.
Right.
C2 can be in parallel with C1. That would have done it also, I think. But here they
No.
R-
That is having no meaning.
Okay.
If you will draw the C1 in the parallel, if you go with the working, that will have the no meaning.
No, but sorry. I mean, I don't want to divert. No, it's clear. Let's continue like this. So because
Okay.
yeah.
Yeah. Yeah. Basically, it's like that. Its gain will be like that. I will just say you that how does gain will look like, so that you can understand that what is baseband or passband. It is like that. Okay.
Correct.
Basically, we have two frequency, FL and FH. This FL will be depends upon high pass filter, and this FH is depends upon low pass filter values. Okay.
Correct.
And this gain they are talking. This gain. Okay. This gain, that is nothing but R2 by R1.
Got it.
Okay. And you have one R2, right? R2 by R1 value in the modulus. If I will take that, will be 57, right? And R2 you have, right? If I'm not wrong, R2 is there with you. That is okay. Gain is 6. Sorry, gain is 6. R2 is 57, and you have to find R1. So you can find basically, right? 57 by R1 will be 57 by 6, right? It will be around 9 point something, 9.1 something.
Correct.
Okay, fine. Any doubt?
No doubt.
Okay, cool. Now again in below question number 2, there is one screenshot you have again added. Design a low pass filter using a capacitor 3.39 and find the value of resistor to provide necessary cutoff frequency. Can we take it as the same as a question number 1?
Yes.
Can't we solve like that only? Because capacitor value is given. Okay, have they give you the frequency? What is the necessary cutoff frequency? Is something missing there?
I'm thinking maybe something is missing. Maybe give me one
Yeah,
second.
what is? Yeah, you can check it.
Okay. Yeah, something is missing on this one.
Or they must be pointing to, or they might be pointing to some other question like that.
Give me 1 second. Let me check.
Yeah, take your time.
Or if frequency is not given, we have to assume something. No, not like that, right? I mean, they have to give, right?
They have to. We don't know, right? We don't know what is the frequency. We can, if we have to design, then we can design that. We can take our frequency as a 1 kilohertz, and we can, if nothing is given, we can do in that fashion, because that is not in our hand, right? So if it's question demands that to provide a necessary, so we can, first of all, we can start our discussion by assuming that let's assume that our cutoff frequency is 1 kilohertz. Since it is a low pass filter, so we can find the resistor.
The question is that much only. I'm just saying, design the low pass filter using a capacitor of 3.3. Oh, sorry. Maybe. Give me 1 second. Let me check here.
Yeah.
Let me paste it correctly. Okay.
Okay.
Okay. The question is wrong. Okay. Let me please delete that. Let me give you 15. Yes, I got it. Okay, 1 second. I think
Both
it has.
questions. No, both question is being wrong. Then
No, no,
you can see.
everything is wrong. I'll tell you. Everything is actually one common thing with two questions. Okay, let me give you
Okay.
the.
Okay.
So please ignore that one.
Okay. Okay.
And
Sure. Sure. Sure.
in Zoom, let me try to see if I can.
Yeah. Here you might have the in the chat you can put it.
Yes, in the chat I've sent. Please take that message and bring it.
Yeah. It's loading. Just 1 minute. Just 1 minute. Yeah. This is your question, right? Visible?
No. Oh, sorry. No, nothing is being shared on
Okay.
your side.
Nothing. Okay.
I want
Let
to
me
paste.
reshare. No, let me. No, pasting will take time then. Okay. Then question number 1, right? Design a low pass filter using a capacitor 3.3 nanofarad.
No. Before this, I think the top one is the question. First, we have to read that part.
Okay. Design an active band pass filter to design a pass frequency range of 400 to okay. Basically, they are telling that their frequency range is 400 to 2400 hertz, right? So what will be the okay? Consist of
Consisting
two
of
non-inverting first stage in series low pass filter, and in first we have the low pass filter. Okay. Again we have a band pass filter. Again we have a high pass filter. Okay.
Right.
Okay. First we have a consist of two non-inverting. Okay. It means that it is not inverting. So basically we have our filter will be non-inverting. If I say, then I can tell that this is my V input. It can be in this fashion. Okay. After that, minus plus, and again they have one register. Okay, they will non-inverting. Okay, it consists of two non-inverting filter stages in low pass filter.
Combination, right? One high pass,
right.
one low pass, right?
Right. So we can take it in. We have to send it to the negative edges. This our negative is.
Same thing that you did earlier, right? It's a combination of both, right?
Right. It's a combination of both. Here we have to take the like that because it is non-inverting, right?
But we can draw the previous one.
No, but it will become inverting because the signal is getting faded there. We have to fade our signal to inverting terminal. Are you getting what I want to say? Okay, then we have to make a feedback register like that. Are you getting my point? Okay, this is your V output. This is grounded. Okay, using 3.3 nanofarad capacitor. So design a low pass filter first. Okay, so what will be the low pass filter FH we consider, right or wrong? What is that? 2400 gigahertz, right or wrong? Are you getting the concept or not? And for this FL is there, right? For high pass filter, name is hi-fi, but we are considering FL, low frequency. This concept you are getting or not?
Yeah, I mean, this one always I get confused because it will sound like the other one, but finally last time, I mean, I did that, I understood, but
it's
now
like that. See, it's like that.
Yeah.
Low pass filter, it means that it is something like that, right? It means that low pass filter will have some high. This is not low pass. This is low pass, right? This is your low pass. Low pass filter will attenuate after some value. That value we are telling that high frequency value, high value. What is FH? Okay, and your high pass will be like that. Okay, let me draw with red. This is your high pass. It telling that after certain frequency, we are allowing the signal to pass. And they are telling that after certain frequency, we are not allowing the signal to pass. Since FH is greater than FL, so we are denoting it with FH.
Got it.
Got it? So basically, you can then directly write the formulas. I think you will get the answer. Let me. Are you getting the answer? FH is 1 by 2 pi R into 3.3 nanofarad. So basically, it is FH is 2 into 3.44, 3.3 into 2400, 1 divided by then. You would be getting, if my calculation is not wrong, then you would be getting around 20.105 kilo ohm.
Yeah,
okay,
got it.
for this one. For this one. So for this register I'm talking. Okay, since gain is not given, so we cannot find this value. We can assume any type of gain. Are you getting me?
I understood that.
Okay. And this FL is nothing but again 1 by 2 pi R into 3.3 nanofarad. But here FL value is 400 hertz, right? And that will be 2 pi into R into 3.3 nanofarad. And that value we can find 2 into 3.14
No.
into.
Sorry. This one is 2.9 nanofarad.
For this, it is given other. Okay, 2.9.
Second question.
Okay, second question. Okay, 2.9.
Got it.
Okay. So basically, it will be what? 2 into 3.14 into 2.9 into 400 divided by 1. 3.14 to 2.9 into 400, 1 divided by 2. What I am getting for this nano is 10 over 19. What I am getting 137.272 kilo.
Yeah. Correct. So the tricky part is, okay, it's just confusing, right? I mean, but we have to understand is, see, earlier for low pass, we had a cutoff. That cutoff is actually
low pass will always having the high cutoff.
High cutoff.
You have to make it clear, because it is the high frequency, it is the maximum frequency after which signal is not getting passed. So that's why we are denoting it with FH. And for high pass, it is the lowest frequency after that signal is getting passed. Are you getting it?
No, it's clear. But
okay, it's clear, right?
When we do it individually, we reverse the names, correct? FL and FH?
No.
Okay.
See, for our convenience, we used to know, but the current notation for low pass is always FH, and correct notation for high pass is always FL. Why? Because I told you, FS is the maximum frequency. In low pass, what happens after a certain maximum frequency, that is the high frequency, after a certain high value of frequency, our signal is getting. So can you tell me, in the low pass, the maximum frequency, allowed frequency will be FH, right?
FH.
Okay.
Yeah, FH and FL will make it. Okay, got it.
Yeah. So basically, when we are taking it in individual, we used to denote with FC, not FH and F1. FC is the cutoff frequency.
Actually, the easiest now it will be for low pulse, always use
FH.
And the other one also is FL. Now here also we will not have any confusion if you use the same convention, right?
Right.
That is the best way.
You will never have that is the simplest. Okay. Fine. Okay, let me open your another question. Other questions are fine, right? Question number 3.
This is pretty much the same, I think, right?
Yeah, this is pretty. This they asked you to derive it, and after derivation, you have to conclude that how it is low pass and how it is high pass. Basically, it is that you can see in 3E, They've asked what is cutoff frequency, right? So we used to tell it as FC. Since we have already studied this circuit 10-15 minutes back, so directly by seeing this circuit, I can tell you that this is low pass filter, right? But the actual way is to find it, you have to derive everything. After deriving, you have to conclude that this is low pass, right?
So VO by VI they asked.
Yeah. So do you know S domain analysis?
Sorry?
S domain.
No.
Frequency domain analysis, haven't you done? Because
No.
this derivation will be done on using that way also. Okay. So okay, let me just brief you. The S domain is nothing but we are converting our circuit into the Laplace form. Okay. In the Laplace form, our V input will be written as V input S. Okay. And V output will be written as V output S. Okay. Capacitor will get changed to 1 by SC. Okay. And resistor will be as it is. Okay. This is the brief concept of our S domain. Okay.
Sorry, can you repeat this part?
Yeah. Basically, they have asked you HS, right or wrong? They have asked you HS, right? They have S term in the bracket, right? So
Yes.
they are asking you to find gain. HS is nothing but a gain in S domain. Okay. In the S domain is nothing but Laplace of every element, Laplace transform of every element, and Laplace transform of every signal. Okay. So I'm telling that your Laplace transform of V input can be written as V input S. V output can be written as V output S. C will be represented as 1 by SC capacitor. Okay. And resistor will be represented with R. Okay.
The only thing changes is in our earlier equations, we have to replace S with C with 1 by SC.
Right.
Okay. Got it.
I will solve it, then you will get to know. Okay. Much clearer. Okay. I will transform my circuit in S domain. Okay. So basically it is like that only. So I will tell it 1 by SC. This is R1. This is V input S. This is V output S. Okay. Any doubt?
No.
Okay. Now, using virtual ground condition, can I tell? Using virtual ground condition, can I say V plus equal to V minus equal to 0? Can I say? In the op-amp, right?
Yeah, correct.
This value and this value will be 0, right or wrong?
Yeah, it is.
Okay. Now apply Kirchhoff's current law at inverting node. Inverting node of op-amp. Okay. So if I name this is current I1 going, this is current I2 going, and this is current I3 going. Okay. So by Kirchhoff's current law, can I say that current entering equal to current leaving is equal to I1 equal to I12 plus I3? Can I say?
Yes.
Okay. Now our agenda is to find I1. Okay. What is I1? Can I say I1 is V input minus 0 divided by R1? Can I say?
Yeah. V by R1. Yes.
It is V input S by R1. Can I say I2 will be 0 minus V output S divided by R2? Can I say?
Yes. Got it. You put everything
Basically,
in
it is.
Okay.
Right. And I3 will be what? 0 minus V output S divided by 1 by SC. Basically, it will be V output S divided by 1 by SC. Basically, it will be minus SC into V output S. Can I say in this fashion?
Yes.
Okay. Now I will put all these values in my equation number 1. Okay. So basically, it will be V input S, R1, V output S R2 minus SC V output S. Okay. So basically it will be V input S R1 V output S 1 by R2 plus 1. Okay. So if I will calculate it.
No. Here.
Have I made some mistakes?
Yeah. That SC has to come, I think. SC. 1 by R2 plus.
Yeah. SCR. Okay. Now what is our requirement? HS, right? HS is what? V output S divided by V input S. Right or wrong? So if I will manipulate it, it will be R2 by R1 1 by SCR2 and minus. Right or wrong?
Right.
Then this is our gain. Okay. This is our part A and this is our gain. Any doubt in this one?
This is our gain in our
S domain. In the S domain. Okay. So they have asked you use the nodal method. We use nodal method, right? We apply Kirchhoff's current law at inverting node, right? And find the transfer function. This is transfer function in terms of R1, R2, and C. It's totally fine, right? Any doubt?
There is no doubt, but I can also, I mean, just if I don't want to simplify, I can also say my VO is in S domain by VI in S domain equal to minus of, I can write, no, you have maximized it a lot. Okay. Can you go a little bit further?
Yeah.
Okay. If I don't want to simplify, I can still write VO by Vin equal to minus 1 by R1
Okay.
by 1 by R2 plus SC. Let's say if I don't simplify it. I mean,
no. It is not SC. It will be the parallel combination. These are in parallel. So how can you write R2 plus 1 by SC?
No. Wait a minute. So let me take control. Yeah. No, the last step I'm just saying. See, if you see minus V by see earlier it was 1 by R2 plus SC is there, right?
Yeah.
It will be 1 by 1 plus SC R2 by R2. It's okay. I thought even if I don't simplify it, it should be the same.
We have to simplify.
That's okay. I'll simplify it. Not a big deal. Yeah. It's clear, sir. Yeah. Let's go.
Yeah. And one shortcut I am telling you. See, what is gain V output by V input? Is always feedback resistance
minus R2 by R1.
Yeah. So if I tell this whole term as X2, so our V output S will be nothing but minus X2 by X1 by R1. And X2 is what? Parallel combination of this one.
That is how actually I did last time.
Yeah. That is the best way. But they have asked you to show the work, so I did in that fashion. Okay. Okay. Now they are asking in part B magnitude of Hj omega. So S is nothing but J omega. In place of S, I will put J omega. Okay. So I will get Hj omega equal to minus R2 by R1. Okay. 1 by 1 plus J omega C R2. Okay. Understood? Now I have to find magnitude. Can you find the magnitude of this one? Magnitude of this one will be R2 by R1. 1 by, first of all, 1 by 1 plus J omega CR2. So this can be written as R2 by R1 into 1 by under root, if I would put omega square R2 square C square. Right or wrong?
Correct. 1 by of x square plus y square we do, right? That is like x.
Right.
Yeah, or a plus I will be
1. Yeah, x is here 1. So y square is omega C into RT whole square. Okay. And since R2 and R1 are only the magnitude term or only the constant term, so we are taking it is as a positive term because anything come out of the modulus will be positive only. Is it fine for you?
Yeah, clear.
Okay. Now in the C part, they have asked you the phase. Okay. So we have Hj omega equal to R2 by R1, 1 by 1 plus j omega C R2. So we know that suppose if my function is something like the x equal to zy, then our phase is tan inverse y by x, right or wrong?
Correct.
So here our phase will be, in this question will be, again same thing, tan inverse omega c R2 divided by 1, that is omega c R2 only. Right or wrong? Any doubt?
Clear.
Any doubt?
Y by x. Okay.
And that is minus, sorry, that is minus tan inverse.
Tan inverse of WCR2. Okay, clear.
Okay. And they have, in D part, they have asked it, is it high pass or low pass? You can simply say that it is low pass. Any doubt in this?
No.
In E part, they have asked you what is the cutoff frequency. So cutoff frequency FC, that is equal to FH, that is equal to 1 by 2 pi R2 into C, that is nothing but 1 by 2 pi, R2 is given 36K, capacitor value is given 15 nanofarad. So if you will simplify it, you will get in 15, 16.
It's okay. This one, it's okay, sir. We can remove it. We don't have to do
Okay.
that.
Okay. So basically, you will get around 294.8 Hertz. Okay. Now for F part. F part is nothing. F part is nothing. Just you have to write everything in the you have to just pick up these values. This one, R2 by R1, and this one. Okay.
It,
okay, and put every values of omega. Omega I am talking, it means that omega you have to put omega equal to 2 pi f. Okay, and for each frequency you can find the gain. Right? Understood. Gain is R2 by R1 into 1 by underscore omega R2 square into C2 into C square. So basically R2 and R1 values is given to you. R2 is 36K. R1
so
value is given to you.
we just do the VO by VI we got. Now the magnitude we are finding, right?
Yeah, this will be the magnitude, and C value is given that it 15, and for F equal to 100 you have to find. After that you have to calculate into dB. That you know, right? How to calculate in dB? You know that one. Gain in dB is nothing but 20 log into V output by V out win. It means that 20 log of this gain.
Okay, sir.
Basically. Okay. Any doubt?
No doubt.
Okay. That's totally fine, right? You can find phase shift also, right? With this formula.
Tan inverse of Y by X we have to do.
Yeah, tan inverse omega C phase is minus tan inverse omega C R2. I wrote everything at one place, so you can get us for every frequency. You can plot it and fill the table, right or wrong?
Right.
Okay. Okay. Can we move to next question? Any doubt in this one?
No doubt.
Okay. Okay. Next question is that question number 1. Design a first order inverting high pass filter with a desired cutoff frequency 350 Hz and passband gain is 6 dB. Okay, passband gain they have told you 6 dB. Okay, it means that they told you A0 in dB equal to 6 dB. So basically, first of all,
we have to get into the reverse of it, huh?
Right, 20 log gain equal to 6 dB. So basically, we have to take the anti-log, that is 60 divided by 20. If you do the calculation, you will get 1.99. Basically, you can write gain is 2. Okay.
Got it.
Log 2, if you can, gain basically is 2, around 2. Okay. Gain, it means that your V output by V in is 10. 2. Okay. Now they are asking inverting high pass filter. Inverting is nothing. Inverting high pass filter looks like this one.
Resistor and capacitor in series.
Right? And one feedback resistor that I denote with R1. This is R2 and C. This is your V input and this will be grounded. This is your inverting high pass filter.
So if you don't want the gain, R1 will not be there.
Yeah, it will be a unity gain. Then R1 will be a just like a voltage follower circuit, right? It will be feedback, but R1 will be 0, right? Resistor will be 0. Resistance value will be 0. That can be represented using short circuit. Okay, any doubt?
No doubt.
Okay, and they are asking, sorry, they have the cutoff frequency, right? Since it is high pass filter, so it will be FL, that will be 350 hertz, right or wrong? And that 350 hertz will be equated to 1 by 2 pi C into R2. Okay, we have the sorry, we have the C value, that is 15 nanofarad. We can find R2 value, right or wrong?
Right.
1 by 2 pi C into 350. So that is basically 1.1 C is 15 nanofarad and it is 350 goes to 9 divided by. If my calculation is not wrong, then it will be 30.33 kilo ohm. 30.33 kilo ohm if my calculation is not.
Correct.
Yeah, it is 30.33 kilo ohm. Okay, now we have this, and what we know, what will be the gain definition of the inverting, any inverting amplifier gain is what? Minus R2 by R1, right or wrong?
Yes, right.
So I can make it R2 and this as a R1. Okay. Minus R2 R1, and magnitude will be what? R2 by R1. And that we concluded that it is equal to 2, right or wrong?
Right. Now we can find the other rest.
We can find R2 will be 2 into R1. That is nothing but 60.66 kilo ohm.
Clear.
Clear? Any doubt?
No doubt.
Okay. So first part they have asked you, okay, they have asked 3 parts. Draw the circuit, labeling V output, V output and all component. We did it. Write the magnitude and phase transfer function. You can do it, right? Okay, 2-stage filter. Okay, I was doing same question. Yeah, first of all, yeah. Find the magnitude and phase transfer function. You can do it, right? Using nodal. You want my help using nodal?
No, nodal, the same formula, right? How the 1 by SC we have to put the resistance and figure it.
You have to put 0 here, and in place of this one, you have to put SC, and you can apply Kirchhoff's current law, and that will be I1 equal to I2, and you will get your answer.
Okay.
Any doubt?
No doubt.
Okay, totally fine, right? Actual cutoff frequency and passband gain based on register value chosen, you can find it, right? Right?
Yes,
and and you can also fill up the table just like the last question, right or wrong?
Yes, I can fill the table.
Okay. Any doubt till now?
No doubt.
Okay. Now the last question, right? Design an active band pass filter. Again, band pass filter is what? Combination of which one?
High pass and low pass.
First will be high pass or low pass? Can you tell me? First be a low pass, right? Right?
Right.
And second will be high pass. Okay. So have they say that do we want first order non-inverting low pass filter followed by non-inverting high pass filter? Same circuit that we followed earlier, right? Non-inverting they are telling. So we will have the V input here. We will have the one resistor here, one capacitor here, this one here. Okay. Similarly, it will pass to this one. We will have the resistors as a feedback. It will get input. This is our V output. Okay. This will get grounded. This is our band pass filter. basically.
Mm.
Okay. Now, what they asked you, they have given you total passband voltage gain, that is 9 volt per 5 volt. Okay. Use as many 5.6 registers possible. Okay. No issue. So first of all, can you tell me what is the gain of this circuit? Suppose this is R2, this is R1, this is RF, this is R. I noted it. So can you tell me what is the gain of overall circuit?
Yeah, it will be minus R2 by R1 multiplied by the second
1
one
plus RF by R. Okay. Okay.
minus R2
Any doubt?
first one, and the second one will be yes, clear.
Okay. Clear. Now they have given you cutoff frequency. Okay. Now you can see again you have to choose that which is one, which is for low pass and which is for high pass. So this one is for low pass, right? And this one is for high pass, right or wrong? Okay.
Yes, correct.
Correct. Have they given something else? They have given voltage gain. Okay. So basically what they are telling that you have these values, so you can tell you that your FC1, that high pass filter, is nothing but 1 by 2 pi R into C is 720 hertz, right? And your FC2 is 1 by 2 pi R1 into C1. Let give its name C1 and C. Where is, have I made mistake? Yeah, I made mistake. This is not the circuit. It will be a 1 and register will be there. Yeah, this is C2. This is again R. Okay. This will be R into C2. Okay. That will be 1.8 kilohertz. See, here you have to do some manipulation. You have to choose this register in such a way that you are getting gain as 9 volt by volt. Okay. And they are telling you in the last line, use as many as 5.6 kilo register possible. Okay. Are you getting my concept?
Yes.
So you can choose that your R is 1 kilo ohm, this R is 1 kilo ohm, and you can manipulate, you can fix other values, and you can manipulate other values like that. Like I can choose that my R is 1 kilo ohm. Okay, my R1 is also, we can choose as a R1 as a 100 kilo ohm. We can choose any value. Okay, they are telling that you can choose as 5.6. Okay. I can choose R as a 5.6, R1 as a 5.6 kilo, and also RF I can choose as a 5.6 kilo. Okay, then I can choose any value of R2, right or wrong, so that my gain is this much. So
Clear.
We R2 by 5.6, it will be 2. Okay, that will be 9. So basically I can choose 9 into 5.6 divided by 2. I can choose R2 if 25.2K, then I will gain that much. Okay. And based on these R value, I can choose C1 also. Right or wrong?
Right.
Because frequencies are given to us. Right? Any doubt?
No, clear.
You can find again the same phasor and all those things, you can find it, right?
Right.
Okay. Okay. Do you want any more help?
No, sir, clear.
And that MOSFET one?
Yes.
Okay. Okay. I was not expecting that these all questions will get finished in this 1 hour only. Yeah.
Actually, last time when the exams came, I was like pretty good at it, and I've completely forgot. So this is almost now I'm like learning, but I have the background of it. So
Right. That's right. No,
after
because in the message you typed na that I should take you as that you do not have any knowledge. So I was
correct.
thinking
But
that
2
it
months
will
back,
take a
right?
lot.
Because of 4 or 5
Right.
subjects, In 2-3 months, I forgot actually most of it. But now when you're selling it, was able to
Yeah.
recollect.
Okay, okay. So we have to design a switching circuit with a logical level MOSFET. Okay. We have a MOSFET. Okay. To switch a 33 ohm load being powered by 15 volt. This is 33 ohm load that being powered by 15 volt. Okay. This is your MOSFET. Okay. And controlled by a 3.3 volt logic signal. Okay. So,
little bit can you give till transistors I've read the theory and I have some basic knowledge of it, but FET
in the MOSFET,
nothing
the
I have
MOSFET. Okay.
just a little
See,
bit.
yeah, little bit I'm talking about MOSFET. See, in the BJT, we have emitter base and collector, right or wrong?
Correct.
Similarly, here we have one gate. Okay. We have one gate, we have drain, and we have source. Okay. We have gain, we have drain, we have source. Okay. But the important thing of the MOSFET in the BJT was current control device. BJT was current control device, and MOSFET is voltage control device. What do you mean by voltage control and current control? Here we are supplying voltage, and this output current will get changed. Okay, but in BJT we are supplying the input current IB. Okay, and based of these IB, these IC and all those things are being controlled. Okay, but here with the VG gate voltage, we are controlling drain voltage, source voltage, and this drain current. Okay, because here in MOSFET the characteristics of MOSFET is that gate current is 0. Okay, and its input impedance is very high. These are the very important and very important feature of MOSFET that are making it very different from BJT.
Yeah, in BJT, the linear section, you'll pass a little bit of current in IB and then you'll get a lot of current in the collector.
Right. Depends upon the biasing and all.
If it's an active.
Here we are controlling, because BJT MOSFET circuit are built in such a way that if you see the working of the MOSFET, that if you supply the gate voltages, it will the electron and hole start to flow like that. So I'm not going to that working, but you have to understand in that.
For us, the bottom line, what we have to remember is some voltage is fed at the gain. Because of that, you are getting some voltage and current in the drain.
In the drain, right? In our output. Okay, and the one other important parameter that in the MOSFET gate current is 0. We cannot drive any gate current to the MOSFET. Okay, correct. Because MOSFET is controlled. Yeah. Okay.
Voltage.
Understood. Okay.
These
are the basic bottom line of the working that you can explain to anyone.
Now it is clear. Now I think I will be able to understand. Yeah.
Okay. And in the MOSFET, we have only one type of current. Suppose it is N-channel MOSFET, we will have the only electron to flow. But in the BJT, we have the both, electron and holes both flowing. Okay, that is okay. So basically, they are telling you design a circuit. Basically, they have given you this 15 volt and they are giving you 3.3 volt. Okay, using a logic level to switch a 30 ohm resistor. Haven't they given any other thing? Have they given some other thing or not?
I don't know. Maybe additional it is saying. So before
it should have the threshold voltage, something like that. Let me think also.
Design a circuit translation. Yeah, that's all they're saying. 33 ohm load. Load is the 33 ohm. Got it?
Right.
15 volt. That part. is also clear. Controlled by a 3.3 volt logic. That is your gain. Okay.
That is your gain. You're not getting what the gain you are talking?
No, 3.3 volts at VG. I'm just looking at
Right.
what the question and what you have filled. 33
Right.
ohms you have given the load, and then it's powered by 15 volts. I don't know, maybe that's all. No, they have to ask some things, right? Like
Right,
how in
right.
the
Yeah, because in the MOSFET, the current equation is ID equal to, because in MOSFET, again, there are different mode of operation. So first of all, we have to check that whether this MOSFET is in active mode or saturation. In MOSFET, we have three modes: cutoff mode, active mode, and saturation mode. In the cutoff mode, the switch is open. Okay, basically switch is open. So we cannot drive any current, and our output will become VCC on VDD only. In the other mode, we have the saturation mode, and we have the triode region and saturation mode. In the saturation mode, our current is given by this value, VGS minus VT. So we are not having any parameter. Either they can give you drain current, something like that, so that we can proceed, or we can, if it is design, we can assume any value and we can proceed. In that way, we can also do. But I'm not, or they are asking you to just draw the circuit. This is also a condition. This may be. I don't know
let me
what they are asking.
give me 1 second, okay? Let me
Okay. Okay.
see
Okay.
what those guys have solved in the paper, okay? So they're saying connect the 15 volt supply to the drain of the MOSFET. Okay.
Yeah.
The
Right.
33 ohm load between the drain of the MOSFET and the ground that you already did. Connect the
Right.
source of MOSFET to ground.
Right. I did it.
The gate of the MOSFET to the 3.3 volt logic signal.
Right.
Add a resistor between the gate and the 3.3 volt logic
Yeah.
signal to limit the current flowing into the gate. A value
Yes.
between 100 ohms to 10 kilo ohms would be suitable.
For okay. They are telling that you can have the 100 ohm to 10 kilo ohm. The RG value. This RG value they have given you.
1 second. I'm not there. Let me. That RG.
This RG value they tell you
100 ohms to 10 ohms will be suitable.
100 ohm to 10 kilo.
Hmm.
Okay, it means that it got designed.
Operation they're saying when the logic signal is at
Okay.
3.3 volts, the MOSFET will be on state, allowing the current to flow from the 15 volt supply through the load to ground.
Okay.
When the logic signal is at 0 volt, the MOSFET will be in off state and no current will. So basically, as a switch they are using. So when you send 0, nothing will flow from.
Right. Yeah. It will switch only. When your input is 0, your output will be 1. Okay. When your input is 1, output will be 0. Basically, in this fashion, that's it.
No, when the input is. No, I think what they're saying is, give me 1 second. Let me read.
Yeah. When your input is logic 3.3 volt, the current will flow.
On state.
MOSFET will be in
On state, allowing
on
current to
state.
flow.
Right.
Supply through the load.
Yeah. Let me show you. If MOSFET is in on state, okay, that means the MOSFET will be closed, right or wrong? On state. On I am talking. MOSFET will be closed, right?
No, it will be
Right or wrong?
a short circuit.
Yeah, and we used to take the output from drain. So this is 1. So what will be output, 0 or not? Because it will directly connect it to the ground. Are you getting my point?
This is
Current
like
will flow.
This is like the saturated region in BJT.
Yeah, just like not saturation. See, MOSFET is connected in that fashion that if we give signal 1 to MOSFET, Okay. If we give signal logic 1 to MOSFET, the current will start to flow, right? MOSFET is in on state. Okay. This MOSFET is in on state. If MOSFET is in on state, that means that current flow from drain to source, right? So it means that it needs a path so that currents to flow, right or wrong? How can you get a path? For getting a path, your MOSFET will be logically behaves like that. How the current flow? If this is your 15 volt, 15 volt, current flows from high potential to low potential, right? What is the high potential? VDD, that is 15 volt. It should try to reach ground, right or wrong? For reaching the ground, this path should be of no obstruction, right or wrong? And we used to take output from drain. Okay, we used to take, just like in the BJT, we have something like that, and we are taking output from this collector. So in this here, we are taking output from drain. Okay. Are you getting my point? Okay. In the BZT, it was like that we have the VCE something values. It was also logically 0. So when we are giving V input equal to 1, it was also V input we are getting as a 0, because it is acting as a switch. Okay. And when switch is in on state, we will get output as 0, as it is as possible. Okay. Any doubt?
No doubt.
Okay. In the off state, how it behaves? In the off state, it will be open circuit. Okay. Current will be 0. And we can take output from here, right? And this output will be nothing but 15 volt. Okay. And 15 volt is logic 1. Okay. So for your logic input 0, logic 0, you are getting logic 1. And for logic 1, you are getting logic 0.
Okay, got
Basically, in this way, it is working. So they may have asked you to explain these things, and design part, you already designed it, that how they are connecting it. Okay. They have asked that much only. Okay.
Okay.
Any
No questions.
No questions. So basically, this is your design.
Got it.
Okay. And for describing, you can describe that it is behaving that way. Which gate? It is behaving like an inverter. Okay. MOSFET here behaves like an inverter. And always MOSFET behaves like an inverter. Okay. There is no if and but. Okay.
Got it.
Got it?
Got it.
Okay. Hope you got everything.
Yeah.
Right?
Right.
Do you have any more doubt for me?
No doubt. No.
Okay. And if you want to learn the Butterworth, I must ask you to share you some notes. Okay. So that I can get to know that how the Butterworth are being designed in your. Okay.
Okay, sir. Okay.
Okay. Cool.
Thank you so much, Abhishek. Bye, Abhishek. Thanks, Aditya. Bye, guys.